Good evening all. Welcome to live session number 9 for Computational Fluid Dynamics for Incompressible Flows. We have covered from the governing equations to starting from the governing equations for solving fluid dynamic problems, the Navier-Stokes equations. We discussed different kinds of boundary conditions, and then we classified the PDEs into elliptic, parabolic, hyperbolic, depending on how the information propagates across time and space. And then in order to solve these equations, we discussed a method called finite difference, which we were discussing in the last few weeks. We applied that particular tool to elliptic, parabolic, and hyperbolic equations. Now the question is, in all of these, we understood that there is something called consistency, stability. There are three terms that we discussed. One is stability. Consistency. Stability is when the errors do not actually grow up. They tend to become stable or they keep on reducing. Consistency is when the grid size as well as the time step size reduced to zero. The solution from your finite difference method approaches the actual analytical solution. When both of these are met, we call that particular solution to be convergent. We already discussed how to verify consistency. You take the finite difference form of the finite difference equations, and then we use Taylor series approximation, then see the truncation error, substitute delta x tends to 0, delta t tends to 0, and if the truncated expression goes to 0, in that limit delta x delta t tends to 0. As both of these tend to 0, the truncation error will also go to 0, then that particular scheme is called a consistent scheme. This we have already done before. The one that we have not discussed is the stability, so that is what we will be covering in this week. So there are different methods. The one that is covered in this week is von Neumann stability analysis for different kinds of equations. For parabolic, we'll do for forward time central space, backward time central space, Crank-Nicolson methods, and for hyperbolic, forward time forward space, forward time central space, Lax-Monroe, Huffman difference. For all of these methods, we'll see how to extend the von Neumann stability analysis and then evaluate the stability criteria for each of these methods. As you can observe that this is not there for elliptic equations, because in elliptic equations we do not have any time term. All that we have is usually the spatial terms, and information has to be simultaneous process. So there the stability in the sense will only depend on the solver, and we will discuss this a little later, where we'll observe how the errors are actually developing, how the errors actually propagate within, say, Gauss-Seidel method, and what are the techniques to understand how this error actually decays as a function of your iteration number. And there are other solvers also that we'll also discuss a little later, not in this week. But for now, we will restrict to parabolic and hyperbolic, essentially in terms of time. How does error either increase or decrease? So this particular analysis is applicable only for linear PDEs. So whenever we have a nonlinear PDE, all we have to do is locally linearize the nonlinear PDEs. So when I say locally linearize, what I meant is, let's say you have a function f of x. In order to locally linearize it, we will expand this around a given point. This will be a constant. X naught is the point we are linearizing that particular equation around, or that particular function. Plus you have just the Taylor series expansion that we have, plus the other higher order terms, which we will ignore. So this will be the linearized form of that particular function. So in the governing equation, we will only use the linearized form and then apply this particular analysis. The constants are assumed to be, the coefficients are assumed to be constant, and the boundary conditions are periodic. What this essentially means, the effect of boundary conditions is not actually covered in this particular stability analysis. All we are worried about is what is happening in the interior of the domain, how the errors are actually growing or reducing in the interior of the domain. So mathematically, what we will do is we'll assume that the error is expanded using Fourier series, and we will understand what is the coefficients of this Fourier term going to be. So for any particular frequency, if that particular coefficient is increasing as a function of time, then increasing or decreasing, that ratio is what we call the amplification factor, which is error at an ith node for n+1 time step divided by error at the same node for nth time step. This we are calling the amplification factor. If this is greater than 1, then as time progresses, the errors keep on increasing. So that particular method is going to be an unstable one. On the other hand, if it is less than or equal to 1, then that particular method is going to be stable. So all we will try to do is we will assume error of this particular form. We will substitute this into the particular differential into the particular finite difference scheme that we aim to evaluate, and then observe what is the value of this amplification factor. Whether it, or in other words, we will understand, okay, for what conditions of certain conditions, or what are the conditions that we can actually derive by by specifying this condition. If I specify the amplification factor has to be less than or equal to 1, what form of finite difference equation, like what are the criteria for this particular condition to be satisfied? That is something that we will derive. So let's say we'll start with forward time center, we'll start with parabolic equations first. So let's say for one I'll do a full derivation, and for others we can actually see how it can be made faster. So let's say we have a parabolic equation, so which is del phi del t is gamma times del square phi del x square. So forward time central space, so phi forward time is n plus 1 minus at the same grid point by delta t is gamma times central space, so we have to use I plus 1, and this is forward time, so it's an explicit method. We can define the current number as gamma delta t by delta x square, and we can use instead of phi, what we would be expecting is we'll have this an actual solution plus some error that is equals to numerical solution. So the numerical solution is the analytical solution plus some error terms. So the analytical solution will anyway be satisfying the original equation, and we know that this particular scheme is consistent. So if I substitute the analytical component into this, the term would actually go to 0. The only thing that is remaining will be the error terms. So I can just write this as minus 2 epsilon I n, this is epsilon I minus 1 n. So all we have to do now is take one term of this particular form. So this will say how the error grows as a function of time, and then I'll have, so this is basically one term within the Fourier series of that particular function epsilon x comma t. So instead of writing is cos and sine and cos, we'll be writing in terms of this Euler form. So e power ikx is basically cos kx plus I sin kx. Or I can write it in a simple way, like let's just call that beta into e power I beta. We'll do that little later. We'll see what beta is and stuff. Let's start with this. So with this we have epsilon I plus 1 is x plus delta x for I minus 1 grid. So we have a grid like this, I minus 1, I and I plus 1. So this is at a given location x. This is delta x. So again we are assuming here uniform grid. So this will be x minus delta x, this will be x plus delta x. So on LH, on RHS we have e power at, all of them are at the same time step. So this will be e power at times we have or ikx plus delta x minus 2 e power ikx plus e power ik x minus delta x. On LHS we have n plus 1, so this will be t plus delta t. I'll take both of them are at the same x coordinate, so e power ikx times minus e power at. So if you can eliminate the term e power at times e power ikx, so that leaves us with e power a delta t minus 1 is current number times minus ik delta x minus 2. So this is what we are calling the term that I have shown here is amplification factor epsilon I n plus 1 by epsilon I n. So this is basically e power a times delta t. So we have a t plus delta t term and a t term here. So we have a e power a delta t. So this is my gain, or the amplification factor is 1 plus times This you can write it as e power I, I can write this k delta x as beta. It will be a little easier to see. So this is basically my cos beta. We can do some other manipulations also, like algebraic operations, where you can expand this into. We have some expression. So first let's understand what is this beta is. So beta is k times delta x. So what does this k signify? So just like we have k is basically the wave number, or in other words, this is basically like saying that whatever error we are going to have is if that particular frequency component of that particular error as a function of space. So if my error is of this particular form, this is my x coordinate. This distance is my 1 by k. So depending on our spatial grid dimension delta x, this beta will be a function of that. And we have different components for this function. Like in the error term, it's actually we will write the error term as actually summation of multiple components. Where this m will be varying for like multiple frequencies. So we can have errors of very high frequency as well as very low frequency. So very high frequency errors are random noise, so which are basically happening at every grid point, and there are some low frequency errors. We'll come back to this again a little later in say next week or next to next week, where we'll explore what is effect of this frequency on the solver we are using. Let's say if we discuss some solvers like say Gauss-Seidel method or Jacobian method, we already observed that they're actually quite slow to converge. We'll understand the reason for that in terms of these values of km. So what happens, like the rate of convergence of this particular algorithm is a function of the value of k that we are going to have here. So that effect is something that we will see, and we'll also exploit that to speed up the algorithms also. But for now, we'll what we are only interested in the stability analysis. So as far as stability is concerned, if for let's say we have n number of these values of k, if any of them, if for any particular value of k, if this particular value of epsilon is actually growing up, then the entire algorithm is going to be unstable. So we'll only analyze as if the solution is valid for all the values of beta, or essentially in terms of for all the values of wave numbers that we can possibly take. So for any value of beta, we know that sine square beta by 2 is going to be between 0 and 1. So the criteria should be such a way that one modulus of g should be less than or equal to 1, which will give me and for this we will be finding the values of Courant number, and this Courant number is the one that we will be interested in. So we know the gamma for this particular problem. Gamma is the diffusion coefficient, delta x is the spatial grid I will be using, say depending on the problem we are solving. Let's say if it is a boundary value problem, then we know it is a parabolic equation. So delta x, of course it is a nonlinear PDE, but we know the delta x from the model requirements. We know the delta x has to be very small, close to the wall, etc. So what is the value of time step that I need to use? So from this we will get the values. So here you can see that gain is a function of my beta and Courant number, which essentially beta is something that has to do with the spatial coordinate grid dimension, and this Courant number is another parameter that we have. So if I can draw a plot between say beta and the Courant number that we have, we can get multiple contours, each contour for different values of g value. So if I fix g equal to 1, I'll get this particular contour. You'll see that. Let's say this is expression I got just now. So where g of g is a function of beta and Courant number is 1 minus 4 times Courant number times sine square beta by 2. So we'll have beta in the range 0 to 2 pi and Courant number in the range 0 to 1. We can go a little higher also, but let's say between 0 to 1. And we plot all the values of g and then make a contour plot. So the figure looks like this. where my y-axis is the current number between 0 to 1, and x-axis is the phase angle, that k times delta x that I just spoke about. So you can see here different values of g, and we want the modulus of g to be less than 1, which means these colors are the acceptable ones. So anything in the red is actually not acceptable. All the values in the blue are the acceptable ranges. So one thing to note here, this dark line is basically the value where the modulus of g is equals to 1. So as you can see, if for all these values, say for if we take a Coulomb number less than 0.5, all the values are in the blue zone, which essentially means this particular scheme that we use is conditionally stable for, so as long as we choose delta t such a way that Coulomb number is less than 0.5, then we will be in the stable region. And if you go higher and higher, then you can see it becomes red, where the amplification becomes greater than 2.5 or something. So which means you cannot integrate infinitely. So after beyond a point, the errors will actually accumulate, and then the solution becomes unstable. So for this criteria, we have Coulomb number less than or equal to half for stability. So this is basically a conditionally stable method. Of course, you do not have to do all of that. You can extend from this. You can just say -1 less than or equal to this thing and see what is the value of Coulomb number for that analytically also. Now, you can see the pattern here. So the idea always is wherever we have a n plus 1 term, we will get all the n plus 1 terms at a ith grid will actually have e power a delta t or the g term coming into them. So this term will actually get replaced by the g term that I have here, and anywhere I have I plus 1 will be replaced with e power ik delta x, and wherever I have I minus 1 will be replaced with e power minus ik delta x. And if I have an n plus 1, I'll have a g coming into it. So accordingly, we can do for all the other methods also. Let's say we'll take backward time central space. So the equation remains the same. So for backward time, we have like basically the implicit formulation of the same equation. So we have phi plus 1 . So as I said, this is the ith grid n plus 1 point. So I'll have a g term here coming. -1 is gamma delta t by delta x is Coulomb number. Phi I plus 1 and n plus 1. Because there is an n plus 1, I'll have a g term. Because there is an I plus 1, I'll have e power I beta minus here I have ith term, so I do not have any, there is an n plus 1, so I'll have a g term. I do not have any spatial term, so this will be 1, and I have a factor 2 here, plus here we have an n plus 1, and we have an I minus 1, so this will be e power minus I beta. So if I take terms together, so g will be having 1 plus 2 minus same as before. We have a 2 times cos beta minus 1. So I can take them on the other side. So g into so and from this we can derive the values of Coulomb number for which small g is less than or equal to 1. Similarly, we can make a plot. So we can also use the same way here. Okay, I think this is minus. So G will be a function of 1 by 1 minus 4 times current number times sine square beta by 2. I'll get back to this a little later. But from this we can derive the values of G. So what would be the values of G such that this, what will be the value of current number for which this is satisfied? Sine square beta by 2 is going to be between 0 and 1. I think there is a mistake somewhere. You have missed something somewhere? Okay, 1 minus cos beta is 4 sine square beta by 2, so this will be plus. Sine square beta by 2 is a positive value between 0 to 1, and we have 1 plus some positive quantity. So 1 divided by 1 plus some positive quantity is always going to be less than or equal to 1. So this is an unconditionally stable. But again, I'm reiterating the same thing. Whenever you are using an unconditionally stable, it means that you can use any value of current number, or in other words, you can use any value of delta t, but the only limitation is going to come from the accuracy of that particular scheme. You can use very high values of current number, but then the accuracy will be depend. For example, if you are using this particular method, it is only first order accurate in time. So use an unconditionally stable algorithm with a higher accuracy time scheme. So that way it would also be stable, and then it will also give you higher accuracy in time. So the limitation in delta t size will only come from accuracy for these unconditionally stable methods. The best example would be Crank-Nicolson method. So if you recollect, what is the finite difference equation for this? I should have shown the other plot here. So this is a function of beta and current number, and these contours are for the values of amplification factor. So you can see all the values within, for all the range of current numbers I have taken 0 to 1. The values are within the value that we need. That the modulus of amplification factor is less than or equal to 1. Just to check, we can also increase the current number. So instead of 1, let's say if I keep 2. Yeah, you can see here also that the values still remain less than or equal to 1. So this particular method is actually an unstable method. Now let's say we'll use the Crank-Nicolson method. I think by now this is clear how to proceed. So all we have to do is we have equal weightages for both explicit and the implicit forms. You have pi plus 1 and plus 1. And then the explicit form 2 pi n plus pi minus 1 n. So as I said, so n plus 1 will have the gain term since it is at same grid point. There is no factor. Minus here both are same, so I'll have 1. This current number by 2 times I plus 1 and n plus 1. So for n plus 1 we'll have the g term, and for I plus 1 we have e power I beta. This is I and n plus 1. So because it is n plus 1, we have a g term. At ith grid we have 1 plus g times I minus 1, so e power I beta. Similarly here, all of them do not have any, all of them are at the nth time step, so they do not have any amplification factor. For I plus 1, I minus 1, we have e power I beta minus 2 plus e power minus I beta. So this will be current number type 2 times 2 cos beta minus 2 and we have the factor coming out. We have 1 minus g by 1 plus g, this current number times sine square beta by 2. So from this I can do component of dividend and write this as a minus b by a plus b. Yeah. So the second, you can see both of these terms are positive. So this particular quantity is always going to be less than or equal to 1. And this is actually second order accurate in time. So this is an unconditionally stable algorithm. We can also observe that from the phase plot here. So let's say for the Crank-Nicolson, we will write this as the amplification factor. 1 minus CO sine square beta by 2 plus 1 plus current number times sine square beta by 2. So the plot looks something like this. Just like the one I showed even for the backward scheme. So in the stability, we wouldn't see any difference, but the accuracy of the scheme is actually Crank-Nicolson is actually second order accurate. Now let's say instead of so this is assuming that both are we are giving equal weightage to both the explicit as well as the implicit formulations. But let's say now we want to make this as a function of some other function. So let's say I write a different scheme where I'll put as pi n plus 1 some function theta times the explicit form. I'll just write this as explicit form plus 1 minus theta times the implicit form. Then what would happen? Like when theta equals to half, I would get back the Crank-Nicolson method. But as I said before, we like that this would actually be a little more difficult to solve. Whenever we have an explicit and implicit formulation, it will be a little difficult to solve, especially with the implicit components. Or I can use the other way around also. But the problem is instead of theta equal to 0.5, we can also use other combinations. Let's say theta equal to 0.1 and theta equal to 0.9. So what would happen to the stability criteria? So will it still remain unconditionally stable or will something happen? Ideally, we would expect as theta tends to 1, it should become more and more explicit. So it should become a conditionally stable one where the coordinate number should be less than or equal to 0.5. And as we go more and more towards the implicit, or in other words, as theta goes to 0, we would expect that particular uh, stability criteria or the coordinate number to be unconditionally stable. So what would happen for any other value intermediate between them? Let's say 0.1 or 0.9, what would happen? Okay, I'll write maximum coordinate number, something like this. So formulation would be same. So this will be g minus 1 is coordinate number times we have it theta times we have just seen what are the terms that we are going to get here. So we'll have e power I beta. I'll just take the term common. E power I beta plus e power minus I beta minus 2 times theta plus 1 minus theta times g times the same term. Is this clear? So all we are doing is we are just taking the step directly from this. So once we do the explicit, we know that we are going to get this term. Sorry, get this term, and for the implicit, we are going to get this term. So I've just written them directly here. So that would become 2 times cos beta minus 1 theta plus 1 minus theta times g. 4 sin square beta by 2 times Courant number times 1 minus theta is. So if theta becomes 0, it is an implicit method. So when theta becomes 0, so this term goes 0. So this is a positive quantity. So G is less than or equal to 1 for all values of Courant number. That is our implicit formulation. And when theta becomes 1, this particular term will go to 0, and this quantity will be same as whatever we got for the explicit. So we can vary these values of theta and determine what is the values of this accordingly. So let's say we keep there is say 4 missing here. One minus cos beta is 2 sin square beta by 2. Let me just write it the same way. We have 4 times, let's say 0.9. I'm taking theta as 0.9. But still it is conditionally stable. Sorry, unconditionally stable for Courant number up to 1. Well, let's increase this from 2. Yeah. So we used a value of theta equals to 0.9, which is close to the explicit formulation, but still the method is actually stable, unconditionally stable. So this is a kind of one that we usually use when we use a solver, like the Crank-Nicolson solver. We use a very high value that is close to explicit, so solving the matrix will be a little easier. When we have an explicit, the formulation is closer to the explicit, then we can actually solve it much faster using say Gauss error or something, which where when you are using explicit formulation, we have seen when we are using these methods that we do not have to solve it in that using, like, it doesn't have to be of this form. When you get to this form is usually in the implicit, we have to solve all the equations simultaneously. But the more the closer towards the explicit formation we are, the little we are the the ability to solve the simultaneous equations will also get reduced. The complexity in solving them will also get reduced. So 0.9 is usually kind of the one that I normally use, so that you have this computational versus the stability thing in your control. So having a value close to 1 will give you computational efficiency, so it will be faster to solve, and having a value still less than 1 will ensure that the algorithm is also stable. So you're getting both these advantages at the same time. Hope that is clear. So this is with respect to the parabolic methods, parabolic PDEs. And then we have the hyperbolic PDEs. So the one that we started last time is del phi del t plus t times del phi del x equals to 0. Again, we have different methods. So the approach is similar to whatever we did just now. So this you can write forward time. So this is pi n plus 1 minus pi n by delta t plus t times it is forward space. We have phi I plus 1. Forward time is an explicit formulation by delta x. Instead of current number, we define here a stability criteria in terms of lambda, which we will write it as plus lambda times where lambda is my p delta t by delta x. This is my stability criteria. So in parabolic equations, we have the current number. The equivalent here is this lambda that we will be using. So just like before, whenever I have an n plus 1 term at the same coordinate, we'll have the amplification factor coming in. So this is both are the nth and ith one, so minus 1 plus lambda times. I have the nth coordinate, so there is no amplification factor. I plus 1, so this will be e power I beta, and this is just the ith term and nth one, so I have 1 to 0. You have g as 1 minus, you just write it as 1 plus lambda times 1 e power I beta. And we have to verify what is the value of lambda such that modulus of g is less than or equal to 1. Just like what we did until now, we can do the same here. So we will write the amplification factor as modulus of 1 minus lambda times e power, so im is basically the square root of minus 1 in Julia times beta minus 1. I've just interchanged these terms. Instead of writing as 1 plus lambda times 1 minus this, I've written as 1 minus lambda times e power I beta minus 1. The remaining everything else is the same. We refined the beta to be 0 to 2 pi and lambda between 0 and 1. Z is basically the value of g that I'm calculating here. This is just the plotting stuff. So if I see the plot, you can observe that the values start from 1. So for any value, for even the values as close to 0 as possible, the values of amplification factor are actually greater than 1. So which means that this particular method is actually an unconditionally unstable method. So basically this is practically not useful. This is an unconditionally unstable, which we discussed last week also. We also gave a little intuition saying that in a hyperbolic equation, again, this is assuming that lambda is between 0 to, like I have generated the data between 0 to 1, which means the lambda is c delta t by delta x is greater than 0. Delta t delta x are always positive, so we are essentially assuming c is greater than 0. So when we have a flow such that the flow is in the positive direction of x, then information is essentially in hyperbolic equation, information is also traveling in the same direction. So if information is moving in this direction, using a formulation where future value will actually be required is going to be an unstable one. So instead, let's say if c is less than 0, then this method should actually work out. So let's say I will, instead of giving 0 to 1, I gave from say minus 1 to 1. You can observe that the values here is actually a stable one. So the modulus of c, or the amplification factor, is actually less than 1 when you have the negative values of this, or essentially saying that c value is negative, flow is in the reverse direction. So instead of forward space, if I were to use a backward space, then this algorithm is going to be stable. But of course, we have only verified till 0 to 1. So for lambda less than or equal to 1, it is going to be stable. I hope this is clear. Similarly, instead of forward or backward, let's say we take a central space method. So for the same equation, let's say we will assume c is greater than 0. We will start with this assumption and lambda is c delta t by delta x. So forward time, pin plus 1 minus pin plus lambda times del phi del x. We need central space, so this will be phi I plus 1 n minus I minus 1 n by 2 delta x. So delta x is absorbed into lambda, so lambda by 2 times this. So same as before, this is n plus 1, this is ith one, so I have a g times 1 minus this is going to be 1 times 1 plus lambda by 2. It is nth time step, so it will be 1 times I plus 1 is e power I beta minus nth time step, I minus 1 is going to give me e power minus I beta. This will give me g minus 1 plus e power I beta minus e power minus I beta is sine beta. 2 sine beta, 2 essentially gets cancelled. And we have to make sure that lambda g is less than or equal to 1 and then find the value of lambda for that. So this is my amplification factor function, and the corresponding plot for that is just. So what can be inferred from this plot? Of course, beta is in radians. So between 0 to pi, we have for a form where, of course, all of these values are actually less than 1. So except for these values here. So very high values of beta greater than pi. So this is 6 is around, this is around 2 pi. So this is around pi. So this line is around pi. So for values greater than, for values of phase greater than, this comes to around 2 pi by 3 or something. this method becomes unstable. But for small values of delta x, its method is actually stable. So it's not like conditionally unstable method. So this is a conditionally stable method. And what is the criteria that we can come to? If I say this method, for example, if I say this method as conditionally stable method, what is the comments or what are the inferences that I can make from this plot? Like there is only certain values of phase for which this method is actually stable. Let's say if I take a value of lambda between 0 to 1, but by definition, as we started out with, we assume that the error term is going to have all the components of the Fourier, all Fourier components. So we do not know what it actually can be. So any criteria that we are deriving should be in such a way that it should be applicable for all the values of phase angle, because we do not know the wave number beforehand itself. So, and for that to be satisfied, the value of lambda should be like any value of lambda you choose, we should have the amplification factor less than or equal to 1. But in this particular problem, there are certain values of beta in which it is 1, and for other values it is not equal to 1. So if you use this particular method, you may actually end up having some solution, but this method in general is actually, like in the strict sense that we define, is actually unconditionally unstable method, because for all values of lambda, this particular equation is not satisfied. For all values of beta, this condition is not satisfied. I think there is no confusion in this. Since this particular stability is essentially like we are assuming that for any value of wave number that we are considering, this particular criteria has to be satisfied. But we can see that there are certain values of wave numbers for which if I choose any lambda here, you can actually end up having an unstable one. So this method is again an unconditionally unstable one in the strict sense. And then we have the other method, it's the Lax-Dendrovsky. If you recollect, for the same equation, let's say. So how did we derive the Lax-Dendrovsky? We started from the Taylor series expansion, and we said phi is phi n plus 1 is phi plus del phi del t plus del square phi del t square, and so on. This will be phi n plus del phi del t can be written as minus c times del phi del x, and for del phi del x we have used the central space form times delta t, plus from the same equation I have phi t is minus c times px. So I can take another derivative, phi tt is minus c times pxt is minus c times ptx. Pt is again minus c times px. This will give me c square px. C square delta t square by 2 factorial times pxx. So this again we will do the second order accurate spatial scheme. So using the same criteria as before, we can get the expansion here. So minus lambda by 2 times pi plus 1n, pi minus 1n, plus t delta t square by x is lambda square by 2. So just as before, here we have the same coordinate but n plus 1 time step. So we will have the amplification factor times 1. This phi n both are same, so this will be 1 minus lambda 2 It's the nth time step, so we do not have amplification factor. It is I plus 1, so we'll have e power I beta minus for I minus 1, we'll have e power minus I beta plus lambda square by 2. The same goes here. I plus 1 will have e power I beta. These both are at ith coordinate and n time step, so we just have 2 plus e power I minus 1 coordinate, so we have e power minus I beta. And all we need to check now is modulus of g should be less than or equal to 1. If we write it down, so we have the amplification factor as modulus of 1 minus lambda by 2 e power I beta minus e power minus I beta plus lambda square by 2 times e power I beta minus 2 plus e power minus I beta. And we'll take the same values of beta between 0 to 2 pi and lambda between 0 to 1.5. I can make this one also. You can see what happens. Yeah, so we need the value of g to be less than or equal to 1. So you can see for all the higher values of lambda, so whenever lambda is greater than or equal to 1, you can see there are certain values of beta for which this particular modulus of g is actually greater than 1. So you can see all these values, it is actually greater than or equal to 1. So what we can infer from this plot is for all the values of lambda less than or equal to 1, we will have for any value of phase angle that we take between 0 to 2 pi, this value is going to be less than or equal to 1. So this particular Lax-Van scheme is a conditionally stable one with lambda less than or equal to 1. Yeah, of course, you can also analytically get to the same value. You can expand this as sine beta, and then from this you can write the cos beta term, and then from there you can do the analytical way of how getting this particular result lambda less than or equal to 1. That is already discussed in the lecture. I'm just showing this another way to infer these plots. So if you have a little more complicated scheme, then you can also use something like this. And again, all these we are discussing only 1D equations. Let's say if you have a 2D equation, we have del phi del x plus del phi del y also in addition to that. Then you'll be having two different variables. So all that would change there is now g is a function of lambda and beta. Now let's say if I also have another variable, let's say in 2D, my equation will be del phi del t plus c times del phi del x plus del phi del y. So let's say I have something of this particular form. Then all that would change is now the amplification factor is going to be function of three variables. I still have my lambda, but lambda we have two different kinds. So we have lambda x, lambda y, and then we also have beta x, which is going to be some k times delta x, and beta y, which is going to be some k times delta y. Ideally, this would also be two different values of wave numbers along x and y directions. Let's say we have a uniform grid and kind of that is symmetric in x and y. So let's say we have only delta x equals to delta y kind of thing. So we end up having lambda and corresponding to betas x and y. If delta x equals to delta y, but only these wave numbers are changing, we just write kx, ky. So something like this, we'll have three variables. So the plot that I have shown here is a 2D one, but now we'll have a third coordinate getting added, one beta along x and beta along y. So you don't have to visualize it. All you can do is generate this matrix C that I have shown here, say for Lax-Van. We can generate this matrix for the values of G for different values. So I just kept beta and lambda here. Now you'll have another variable and then add for loop for that and then generate these values of Z. And from there you can see whether the value, the modulus of this particular value is actually becoming greater than 1 at any particular value or not. And accordingly derive whatever you have. I think that is straightforward. The last one is the upwind differentiation scheme. I think by now the method is straightforward. So let's take the same equation and let's assume C is positive. If C is positive, what would be the upwind scheme? This is straightforward. So I have two possibilities here, plus lambda times what would come here? So the flow is in this direction. So as I said, like whenever we have flow in given direction, in hyperbolic equations, we have to take the coordinates in that particular direction itself. So information will be available flowing from this direction. So I have to use the finite difference in such a way that I use the previous grid points. Like if flow is in this direction, I should use it in such a way that these two grid points will be used. I should not use anything that is going to be in the next spatial location. So if the flow is in the reverse direction, say the flow is happening in this direction, then I would be using this two. We are assuming C is positive, so along the positive x direction. So this will be backward space. So the same as before, n plus 1 time step and ith coordinate, and have my amplification factor. So this is ith coordinate and nth time step, so 1. I minus 1 coordinate will have e power minus I beta. It is nth time step, so there is no amplification factor. This again we have modulus of c should be less than or equal to 1, and from there we'll get the values of lambda. So if we extend the same way for up point, so we have g is 1 minus lambda times 1 minus exponential of minus I beta, and then remaining everything is the same. Beta you have different values, lambda you have different values, and if I make a plot, you can observe the same thing as we saw before. For all the values of lambda less than or equal to 1, you can see that the modulus of g is actually less than or equal to 1 for all the values of phase. Whenever lambda is greater than 1, there are certain values of beta for which the amplification factor is becoming greater than 1. So this particular method is a conditionally stable method with lambda less than or equal to 1. So like up until last week, we have only said that these methods are so and so without actually deriving whether they're actually how to say whether they're stable or not. But now using the von Neumann stability analysis, we can actually confirm whether whatever we discussed in the last week is correct or not. And the last concept that is discussed in this week, we also discussed this last week, is the difference between dispersion and dissipation errors. So this is kind of a quick recap. So whenever we have some differential equation, let's say we start with the hyperbolic equation alone. Let's say I have something like this. You convert it into some particular form, the finite difference form. If we are using, say, the up point differential scheme or Lax-Randolph or any other method, we will have a truncation error term. So if this truncation error term has an even derivative, or it can have an odd derivative in the leading terms. So truncation error will have multiple terms. So it will have this will have some term corresponding to phi xx, some term corresponding to phi triple x, and so on. It will have all these terms. So if we take the leading order term, if the leading order term is a second order derivative, or basically is an even derivative, then what would happen is this equation will become something like you have pt plus c times px plus, or usually some constant term times phi xx. So the truncation error will have this term coming into picture. So this equation, if you compare with, say, the Navier-Stokes equation that we have in 1D, so del u del t plus c times del u del x is basically u there. This is the del square u del x squared term. So the term that is going to be in bracket is something similar to the viscosity term. But here we call this the artificial viscosity because this is introduced because we kind of converted the original PDE into the discretized form, into the finite difference form. So whenever we have this even derivatives, you can always write it in this particular form, and you will end up seeing the effect of this leading truncation error term as an artificial viscosity term. So then what will happen is then you will not have a sharp boundaries, and these boundaries will actually get little smoother. And the constant here is going to be a function of delta x. So as you refine the mesh, if you are using a consistent scheme, this constant will actually go to 0, and you will ideally get a good solution. But obviously, we are not going till delta x tends to 0 or something for all practical purposes. So we will have some artificial viscosity introduced into our solution, into the finite difference solution. But on the other hand, if, for example, you are using some other scheme in such a way that you can eliminate this double derivative coefficient, So you can say we did this last week when we were doing with the lax Van P. If you do the Taylor series analysis in the truncation error term, the coefficient for this double derivative will actually turn out to be 0. But then what happens is instead of a double derivative, you will end up getting some non-zero coefficient for the triple derivative, which is an odd derivative. So this is dissipation. So whenever we have these odd derivatives, what happens is we have seen last week also that this introduces some wiggles. Or in another way, we can do this. We can say that this actually changes the phase speed of this particular problem. So let's say if P has a solution, something of the sort, I think we considered e power ikx minus omega t, something of this sort. So this is, let's say this is one of the harmonic solution for this particular problem, e power ikx minus omega t, or e power minus, I think one of them is forward traveling wave, kx minus omega t, I think is a forward one. So ideally, we would expect the phase speed of this to be Vp, let's the phase speed is omega by k, should be equal to c, whatever the speed that we have. So what this means is for any wave number that you have, all of them will actually travel at the same speed. But what happens is, let's say if you take the derivative, Pt is going to be minus omega, so we have I omega times P, Px is going to be Ik times P, P double x or double derivative is going to be minus k square times P and P triple x be minus I k cube and so on. So when we have a double derivative, there will be these imaginary terms and then there's real terms, so we don't have to worry about it. Whenever we have an odd derivative, these I terms will actually come up together. So we'll end up solving for something like this. We want a non-trivial solution, so we have minus omega plus ck is minus k cube. So if I write this as ck plus k cube is omega, or in other words, Vp, my phase velocity is omega by k is c plus something. I want this term to be actually 0, but instead of being 0, I'm getting some additional quantity. Like if I do this is, which is a function of wave number. So the point that I would like to highlight here is this phase velocity is now becoming a function of the wave number. So as we, let's say the error analysis that we did little before, where we treated error as having several components of Fourier series. So each component of the error term will actually now have a different phase speed. So what happens is as you march in time, as the time increases, so initially, let's say you have something like this, everything will have a certain component, like this is the initial at t equal to 0, this is how the solution looks. But as time progresses in hyperbolic equations, this particular wave should move forward. But then this particular wave will have multiple Fourier components in it. Like if you expand this into the Fourier series, you'll have a certain coefficient for the sine x term, sine 2x, sine 3x, like that we have different terms in Fourier series, right? Now each one has a different wave number, and the phase velocity is going to depend on that wave number. So all of those waves will actually travel with different velocities now. So what happens is there will be some wave which is, let's say, used with two different wave numbers. So there will be some error terms which have a higher frequency. Of course, their amplitude might be a little less, but whatever the smaller amplitudes they have, all those amplitudes will actually show up separately. So you will see some other components coming up here, which are not really existing, but these are coming up because they're traveling at velocities higher or lower than the one that is the original solution. So that is what we call wiggles, which we have seen last time when we used the Lax-Weintraub method. So if you recollect last week when we solved this problem for the dispersion error, you can see these small things that is coming up here. Or even the Lax-Weintraub scheme. You can see initially it will be like this, but error terms will actually come once. This is the original solution. You can see these small terms and you can see how they actually propagate, what happens to them. they are actually, what these are actually are the smaller waves or the error terms that have, which have a different frequency than the original solution. You can see how these are actually propagating within the domain. So this is the dispersion error. So this is happening essentially because you are having different components of the error propagating at different speeds within the domain. Sorry, this is dispersion. The name is similar to whatever you would have collect from your +2 or something when we have the light dispersion. So let's say there is a prism or something, and some particular light wave in white color passes through the prism, it gets split into different colors, essentially because each color or essentially each frequency has a different speed in the domain. So that, this is something similar to that. Each component of error has a different speed within the different speed, but it's not in the reality, but in the way that we use the discretization. Within the finite difference form, each wave or each component has a different speed, so we end up having these small figures. Now what we can do is, one trick is, we don't want both of these. So the way to reduce this is essentially, this is also going to be a function of delta x. So you make delta x as small as possible so that this error or whatever these things are very small in amplitude compared to the other ones. That is the one way that you handle this. The other way is you can come up with some smart difference scheme where you have a certain weightage, known weightages to them. So say a1 and a2 in such a way that the summation of these terms is actually reduced, like to 0. So such that a1 pxx plus a2 p triple x equals to 0. If you can make this equals to 0, all other higher terms, the fourth order, etc., will have delta x to the power 4 or something. Those contributions will actually be very less. So instead of going delta x to be 0, we can use a little higher value of delta x and still end up getting accurate solution in terms of without any dissipation or dispersion errors. But these schemes again, as this a1 and a2, again, if the particular equation that you're solving is nonlinear, then this a1 and a2 are going to be function of the solution that you're trying to solve for. It gets more and more complicated. So we'll not go into all of that. So the idea here is there are ways to, or tricks to essentially make this equal to 0 other than making delta x equals to 0. If you are interested, you can look upon those methods also. So these are the main topics that I discussed this particular week. So I've taken some problems from the previous year exams pertaining to this particular topic. We can go through them so you can answer them, so it will be a little faster. So the von Neumann stability analysis is applicable for which of these conditions? Or essentially these, you can also call them as the limitations of this particular method. It is only applicable when we do not have to deal with the boundary conditions, which is the periodic boundary conditions and a linear PDE. Of course, for a non-linear PDE, you can always linearize it using Taylor series expansion as I told before, and then convert into linear PDE and then solve for that linear one. Again, we also have other conditions that all the coefficients have to be constants, etc., etc. If they're not constant, again you have to kind of locally find a solution. So for a given values of these constant, or for a given values of these coefficients, you can do this analysis. So you can see quickly that this particular method, say if I want to apply this to say Navier-Stokes equation, so we have the momentum equation, say the 2D case. Say something like this. You also have in Navier-Stokes equation, you also have the Laplacian term, and let's say the other terms, pressure term and gravity term. But you can see that it has a time value, it has this advection component, so which is this is something like that. If the advection is negligible, this is similar to our parabolic equation. If you have advection, that is, if advection is dominant, it's like hyperbolic or something and so on. But the problem is this is nonlinear. So the coefficients that we are having can actually, so if you have some fluid where mu is also a function of velocity, or let's say you are solving mutual convection, you have this additional density term coming into picture, which is a function of temperature, which is another equation that we have to solve. So in all those terms, the constants may not be, the coefficients may not be constant. Then we have to locally solve for each and every possible case what is the stability criteria for that. So what we usually do is we use an unconditionally stable methods with as little low delta t or delta x as possible, and then you do a parametric study by varying this delta t and actually seeing that the solution is actually consistent as delta t goes to 0 and your grid spacing goes to 0. So though this analysis looks good on paper, it as the geometry becomes complicated, as your boundary conditions become complicated, the application of this analysis for practical problems is kind of limited. We can get an estimate to start with, but still we have to do the mesh convergence or the time step independence kind of studies to verify whether our particular setup is correct or not. Okay. Which of the following statements regarding dispersion error in numerical methods is true? We discussed this just now. So which of these is true? Dispersion error arises from even derivative terms in the truncation error. It causes artificial smoothing of numerical solution. It arises from odd derivative terms in the truncation error. It does not affect the wave propagation in the numerical scheme. So as I said, dispersion is about when the phase speed changes for different kinds of wave numbers. So that happens because of odd derivatives. So dispersion happens. So there are three things the question discusses about. One is the derivative kind, so even or odd. The other is about the effect on the solution, which is either smoothing or we can have wiggles. And the third one is on the wave propagation. Here we have no effect. And the other one actually affects the phase speed. So I can just call this as phase speed. So for dispersion, we have odd terms and it will actually introduce wiggles. So in this particular, the answer is this, but you can also see the other one. So if even derivative is the dissipation error, and dissipation error causes smoothing of so that you do not have sharp gradients in your solution, and it does not affect dissipation does not affect wave propagation, but dispersion affects the wave propagation. This is dissipation. I think that is straightforward question. So this also we discussed how can the limitations of non-Newman stability analysis be partially overcome for nonlinear PDEs. Whenever we have a nonlinear PDE, we have to locally linearize the equation and then extend the analysis to the linearized form. We also have this matrix stability analysis, which we did not discuss. Maybe if there is some time, we'll discuss next week about how to do this one. But people who have already done some linear algebra or something would know about this already. Whenever you have, so essentially what we are trying to do when we do this finite difference equations is we are trying to convert our original PDEs into eventually a form something like Ax equal to B. So the question now is, when I have to solve this form Ax equal to B, we can comment something about the matrix A. There are some metrics that can actually tell us whether this solution is going to be stable or not. Who are interested in linear algebra can go through those techniques. How do we define that? How do we calculate the stability of this matrix A and so on? They have something called condition number and so on. How to evaluate condition number and anything. All of that is kind of not related to this particular, not required for this particular course. I'm not going through them. So as long as you understand this one, it should be fine. Yeah. Because I think we didn't discuss elliptic equations. So whenever we are having elliptic equations where there is no time term, the entire von Neumann stability analysis, if you see, we are only worried about something called the growth amplification factor G, which is defined something as e power a delta t. So this has something to do with time. There is nothing to do with space or anything. So when we have elliptic equations where there is no time term at all we have is something like let's say the heat conduction or the Laplace equation Pxx plus Py equal to 0. When we have something of this particular form, then we do not have this time a delta t or growth coming into picture. Then also we have some instabilities or then also we can actually end up having divergent solutions. Essentially, the solution will not converge. Okay, in the sense that the errors will actually keep growing with the number of iterations. So what would that depend on? Will it depend on delta x, or how do you kind of ensure that you actually reach a stable solution? That in order to understand that, you have to understand this matrix A that you populated by something called condition number, which will decide whether you'll actually get a solution or not. Which we did not is not covered in this particular week, but we can take it up in next week. Or if you're interested, you can also look up on that how to kind of estimate the condition number of this matrix and how that affects the convergence of your solution for elliptic equations. Okay, what does the Lax equivalence theorem state for linear PDEs? We started out with this particular theorem, which says that you have a PDE, you convert it into a set of finite difference equations, and when you convert it, you use some kind of grid, some kind of delta x delta t to convert this into finite difference equation. So now the solution of this PDE to solution of this FDE. So if I convert from a PDE to FDE, what is the criteria that will ensure that the solution of the actual PDE is equal to the solution of the FDE? So what is the condition for equality between these two in terms of this is what the Lax equivalence theorem states, that if you have a consistent algorithm, consistent and a stable, you will get convergence. Where consistency essentially states that your truncation error will go to 0 as your delta x comma delta t tends to 0. And stability says that your amplification factor is less than or equal to 1. When you choose a scheme such that these two conditions are satisfied, then you will get convergence. This we have also already discussed before also, so I don't think there are any problems in this. This we just discussed, which process ensures that the discretized solution approaches exact as the grid spacing and time spacing tends to 0. These are all the questions I have taken from previous year assignments and exams. So to those of you who are appearing for exam, you can expect the same level of complexity in the problems that you would expect in the final exam. In von Neumann stability analysis, the solution is expanded using which of these? Oh, I think okay, the options are given wrong, but the idea is the solution is expanded using, these are wrong. I'll correct this when I upload the slides. How did we expand the solution? So we started out that the solution is going to be a summation of Fourier series terms. So we have taken several Fourier series terms, and each component we analyzed the amplitude of these components. So that was what was intended to ask, but I think somehow this got messed up. I'll correct this when I upload this into the folder. Okay, comment on the stability of the explicit forward time central space scheme applied to linear convective equation. So what is a linear convective equation? Maybe if I would have written advective, it would have been straightforward. Yeah, ideally when I say convective, it is conduction plus advection, so it should also have a diffusion term. So let's say I have something of this sort. If I would have just said advective term, then it would just have c times del phi del x equal to 0. It is a hyperbolic in nature. Now it has both these terms together, but the method says you have to use explicit forward time and central space. So how would that look? So I'll have pi n plus 1 minus pi n by delta t. Central space, so this will have pi plus 1 by 2 delta x. Explicit, so I've used the n time step values. Again here del square phi del x square, second order accurate if you use central space, pi plus 1. Now if you want to do the analysis just as before, so n plus 1 term, so I'll have the amplification factor minus 1 plus c delta t by delta x, I'll have lambda by 2 times nth coordinate, so there is no amplification nth time step, so there is no amplification factor. I plus 1, I'll have e power I beta minus I minus 1, so I'll have e power minus I beta is gamma times, so I have here gamma times delta t by delta x square is my current number times n time step, and all of them are explicit, so I do not have amplification factor here, but I will be having I plus 1 I and I minus 1, so I have e power I beta minus 2 plus e power minus I beta. So G is going to be 1 minus lambda times e power I beta minus e power I minus I beta 2 is lambda sine beta, and I have Coulomb number times, this is 2 times cos beta minus 2, and write this as 1 minus lambda sine beta minus 4 times Coulomb number times sine square beta by 2. So what can I comment on this? So I need to check whether mod G is less than or equal to 1 or not. So if you want to do this, so I have modulus of 1 minus lambda sine beta minus 4 times Coulomb number times beta square sine square beta by 2. Okay, in the exam you do not have access to this. So how do I solve this? I think when I meant convective, I was only discussing about the advection form. So if it was just advective form, so what would that be? So modulus of 1 minus lambda sine beta should be less than or equal to 1. If Coulomb number is less, then we have minus 1 less than or equal to minus sine beta less than or equal to 1, minus 2 less than or equal to minus lambda sine beta less than or equal to 0. Now depending on whether sine beta is positive or negative, we have two other options. So let's say if sine beta is positive, then we have minus 2, it's a positive quantity, so I can just say lambda times sine beta is less than or equal to 2. And if sine beta is negative, so this quantity is going to be, no, here itself I got that this is unstable method. Okay, C greater than 0. So for C greater than or equal to 0, this value can be again negative or positive. So we have multiple terms here where we always know that lambda should be positive. So this itself is not true. So this is not a stable, like we do not actually get a value for lambda for mod G less than or equal to 1. But if I were to simplify this little further, from this equation I can directly write that G is always less than or equal to 1 minus lambda sine beta, something like this. Because sine square beta by 2, like this particular quantity is always positive, so I can write it as G is always greater than or equal to 1 minus lambda sine beta. So the maximum value of 1 minus G is going to be limited by this. So if I analyze from there, 1 minus lambda sine beta should be less than or equal to 1, where if this particular quantity is always less than 1, then G greater than or equal to, like In order to satisfy that, I do not have any criteria for lambda. I need lambda to be positive, but this can actually go negative for certain values of beta. So there are certain values of beta for which this criteria is not satisfied. So if this criteria is not satisfied, then we do not have the stability to be stability satisfied for this particular equation. So this particular method is not conditionally stable. Also, this is actually an unstable method. Is this clear? I think I confused a little bit in between. Just start again. Let's say this is the equation we have. So what we are trying to do is find whether this mod g is less than or equal to 1 or not. So we specify the condition. But because we also have this current number, we know for sure that this particular quantity is always positive. So I'm saying g equal to this can be replaced with g greater than or equal to 1 minus lambda sine beta. And we need g to be less than or equal to 1 also. But g is greater than or equal to this thing. So which means this term has to be less than 1. So I substituted that here. If this quantity has to be less than or equal to 1, there are certain values of beta for which this particular criteria is not getting satisfied. So when beta is say greater than pi, then this value turns out to be negative. So lambda has to be negative. But by our definition, if c is positive, lambda is basically c delta t by delta x, which can never become negative. So which means this particular criteria will not be satisfied. So in those reasons, g value will be greater than 1. So if for any value of beta, there is g value that is greater than 1, then we can call that particular method to be an unstable one. It's like the criteria for lambda should exist such that that is true for all the values of beta that are possible between 0 to 2 pi, which is not satisfied in this particular problem. I think it is clear. Okay. Okay, this is again a conceptual question. Stability is a property of a PDE or a discretized equation or the modified equation or the analysis method. So as we discussed, stability is something we are discussing about something called stability only because like by default we are assuming that the PDE is stable in the sense that PDE actually has a solution. If the problem that you are solving does not have a solution or has a singularity in some way that if it doesn't actually converge to a solution, then there is no point in discussing. Like even if you use any stable method, you will end up with some non-physical solution. So the first step is we are assuming that the PDE itself is stable, and all these analyses are starting from that assumption. If the physical solution itself is not stable, then none of this is valid at all. So the stability that we are discussing here in this particular week, whatever we discussed up until now, is only for the discretized equation. So we discretized in using some particular scheme. So for that particular scheme and for that particular discretized equation, we applied the stability analysis and we derived at what are the different limitations in terms of delta t or delta x that I have to use so that I'll actually reach a solution. So PDE stability is something else which we are not discussing in this course. We are assuming by default that the PDE describes the physical solution which is stable. It's only for the discretized equation that we discussed up until now. Yeah, I think this question got replaced here. In von Neumann, we did the Fourier series expansion. Yeah, the amplification factor G for a function u of xt to perform von Neumann stability analysis is determined by, as we discussed in the starting itself. So this is something that relates to the error term at a given grid point for n plus 1 time step divided to the nth time step. So this is the amplification factor. Yeah, these are the questions I have. So basically to summarize what we discussed this week, we started out with why we needed stability analysis, especially for time marching solutions for parabolic and hyperbolic equations. We derived that we will only focus on something called amplification factor, which is the ratio of the error term at n plus 1 to n time step, and ensure like what are the criteria of the particular scheme that will ensure this particular amplification factor is less than or equal to 1. And in order to do that, we expanded the series using Fourier series, and we understood that if you are using a consistent scheme and if this particular value of amplification factor is greater than 1 for at least one of the modes in the terms, I mean this km value for at least one of the wavelengths, then the solution becomes unstable eventually. Like if you march infinitely, then eventually it becomes unstable. So instead of doing for the entire series, we only took one element in that series and we solved for that. So what we did is we expanded the finite difference form, and then for all the I plus n plus 1 term, we'll have the amplification factor coming into picture. For all the I plus 1, we'll have some I beta, where beta is k times delta x. and for I minus 1 terms, we'll have e power minus I beta. And eventually from there, we derive the values of G. And then here we made some plots also, but other than that, the criteria is to understand what is the Courant number, or for case of hyperbolic, the stability criteria in terms of lambda, whichever it is, and verified whether they are getting satisfied. For parabolic, we use the Courant number, and for hyperbolic, we use the lambda. So for a given spatial discretization or for a given delta x, we will have the maximum value of Courant number. This we have a limitation on max Courant number. Similarly, here we have a max lambda. That will give you what is the minimum time step size that you have to use so that you will get a stable solution. We have did this for different methods: forward time central space, backward time central space, Franklin cosine implicit and explicit. Similarly, here also explicit and implicit methods we have done that, and we have identified the criteria for lambda. So, finally, we have done a revision of dissipation versus dispersion errors. The key takeaways are: this is for the odd derivative, dissipation is for the even derivatives. Dissipation is basically smoothing out or artificial viscosity term, which comes with the even derivatives. Dispersion comes with the odd derivatives, which is basically some kind of wiggles. This is happening because each mode will actually travel with a different phase speed, and this is basically causes smoothing, or basically some kind of erasing effect of the sharp gradients. So these two errors we discussed, and I have shown you some plots of this where as a function of phase number or whatever the phase that k times delta x that I have shown versus either for parabolic Courant number or the stability criteria, and we have seen contours of the values of the amplification factor, and from there we identified whenever that can be used for say extending it to other say from 1D to 2D or 3D methods. This becomes more and more like you'll have additional dimensions, but you can use that to understand how the value of this amplification factor changes for different values of the stability criteria for Courant number or whatever stability criteria you are using. And then we also discussed some previous year problems pertaining to this particular topic. Yeah, I think here these are the ones I have for this week. Do you have any questions? I think next week we'll start with the stream function vorticity formulation. So we'll actually get started with the Navier-Stokes equation also eventually. But yeah, these are the things I have for this week. If you do not have any questions, then I think we can conclude the session for this week. Yeah, I guess there are no further questions. Okay, thank you for joining, and we'll meet next week. Just highlight the ones that we have covered up until now. So then next week we will discuss this stream function vorticity formulation, which is actually useful for all that. Most of the 2D problems can be solved with this, but there are some challenges with that also. We'll discuss that next week. Thank you for joining. We'll end the session for today.